Today we're talking about section 2.2, which is limits involving infinity. So the first ones we're going to talk about are finite limits, which means they have an actual limit, a value. And so it says the line y equals b, which you should recognize is just a horizontal line, is a horizontal asymptote of y equals f of x if either of the following occur. So the first one that we write is that if we talk about the limit of that function as x approaches infinity, so as x gets bigger and bigger and bigger, the function starts to approach b, that particular value. And I'm going to put and or, because only one of these has to be true, but both can be true. The limit of f of x as x approaches negative infinity could also be b. So what that looks like on a graph, if I were to sketch a picture of that, is if I said here's b, y equals b, my function as x gets infinitely large could approach it. It could also look something like this from the bottom. So as long as it's approaching that, so as x gets toward infinity or toward negative infinity. So we're going to look at the graph of x over the square root of x squared plus 1, and we're going to describe the end behavior using proper limit notation. So go ahead and do that a moment and tell me what is the end behavior as x gets infinitely large and as x gets infinitely small. So I sketched a picture. Here's what it looked like on my calculator, but I can see that it doesn't go too far. So when I look at my table on my calculator, I can see as x gets negative, I can see it's approaching -1. And if I go the opposite direction, again, I can just use my table set, and I want to start it at 12. I could even start it at 120. Because that's x getting larger and larger. I can see that that side's approaching +1. So the way I would write that, I've got this horizontal asymptote here. I've got a horizontal asymptote here. They're different. But the limit of my function as x was going to positive infinity was approaching 1. And the limit of my function as x went to negative infinity over here was -1. They don't have to be the same. All right, so example 2 says I've got this limit as x goes to positive infinity of 5x plus sine of x over x. So this one, it says use the properties from section 1. Sorry, I didn't give you much space here. But we can break this one up. So this looks like 5x over x plus sine of x over x as x gets infinitely large. Well, 5x over x, we should notice that these cancel out, so I end up with just 5. And sine of x over x, I don't really know what that one does, so I have to look at my calculator. So I'm going to go ahead and graph it and do sine of x over x. And please make sure you are in radian mode always. And then when I graph that, I want to know what's happening as x goes to infinity, and I can see it kind of did one of these weird little doohickeys here. But as x is getting bigger and bigger and bigger, I can see, sorry for the bells, it's bouncing back and forth, but I'm going to go to an even bigger value. I'm going to start at 1,000. And this e -4 means it's scientific notation, so it's times 10 to the -4th. So I can see this is getting closer and closer to 0. And I could just keep investigating, but I think that's good enough to see that that one is tending toward 0. So the limit here would be 5 plus 0, which is 5. Now similarly, infinite limits. This time, though, we talk about vertical asymptotes. So you can even look at my little graph that I did over here earlier. You can see these were approaching some sort of vertical asymptote. Our horizontal asymptote describes that end behavior, what's happening as x gets infinitely large or small. But the vertical asymptote refers to what's happening kind of in the middle of this function. So I'm going to sketch that similar picture again. This time I'm going to say, all right, here's x equals a. And I can have a function approaching it one way or another. So this particular graph, it says the limit of my function, but this time instead of saying as x approaches infinity, I'm going to say as x approaches a, and I can't just say a, I have to specify a direction. So I'm going to put either a little minus or a little plus up here. Now I'm going to use my particular graph, my function, as x approached a from the left. This one was going to negative infinity. But I want you to note it could be either positive or negative infinity for an answer there. On the same thing, we could go up on the right-hand side, limit of f of x as x approaches a from the right. In our picture, as we approach a from the right, it's going to positive infinity, but again, I can get either one of those as an answer here. So I want you to find the vertical asymptotes of tangent of x. Just write out, where are the vertical asymptotes? So tangent looks like this. It goes through the origin, and then there's an asymptote at negative pi halves, positive pi halves, 3 pi halves, 5 pi halves, etc. So the distance between those two asymptotes is pi. And so I just said, hey, let's start at pi halves and then just keep adding pi over and over and over again, because this distance is always pi. So my asymptotes are at x equals pi halves plus or minus pi n. All right, end behavior models. We talked about these a lot in pre-calculus. We talk about what happens at the ends. And in pre-calculus, you guys came up with some models that said things like if they have the same power over the same power, that meant something. If I had a higher power over a lower power, that meant something. And if I had a lower power over a higher power, that meant something. So what I want you to do is try to recall that, try to play around with a couple of them. There's going to be a question that's going to pop up. What happens and what kind of answers do you get for each of these scenarios? All right, so when it was same over same, you get that coefficient, that leading coefficient, number divided by number. For high over low, those go to infinity, and that low over high goes to 0. So we're going to talk more about those in a little bit. But here under this end behavior model, it says let f of x be 3x to the fourth minus, and then it kind of gives the rest of this polynomial. And then g of x is kind of this parent function, just plain 3x to the fourth. And it says as x gets infinitely large, what happens to f and g? And so it says to graph those in y1 and y2 and then look at the table of values. So go ahead and enter those in. And then when I look at my table, I'm looking at 0. And there's not much exciting happening. They're quite different around x equals 0, but they didn't ask me for x equals 0. They said as x gets infinitely large. So again, I'm going to use that table set function, and I'm going to start at something large. Let's do 1,000. And look at my table. And oh, I can see that those look pretty identical. And I kind of am curious, what if I had started at maybe only 100? Would I have seen that same type of thing? I can see that it's starting to get there, but not quite. So remember, 100 is not infinitely large, neither is 1,000, in fact, but 1,000's getting bigger. So as x got infinitely large, what we can notice is that the limit of f of x, as x was getting to infinity, was equal to the limit of g of x. as x went to infinity. And in fact, they were both equal to infinity. They're getting infinitely large. So we want to determine end behavior models. So the function g would be considered a right end behavior model if I took both of these functions and divided them, put f divided by g, and I get an answer of 1. So in this particular case, if I did 3x to the fourth minus 2x cubed plus all of that goodness, divided by 3x to the fourth, and I do the limit as x goes to infinity. So something you talked about in pre-calculus was as x gets infinitely large, all of this other noise becomes really insignificant. The one that we really need to focus on is that higher power. So in this case, 3x to the fourth divided by 3x to the fourth is in fact 1. So we would consider 3x to the fourth a right end behavior model, which means as x gets infinitely large, I can just use this to model this entire function. Now, same thing works for left end behavior model, but I would have to use as x goes to negative infinity. Well, the same thing is going to happen here, where I'm going to get 3x to the fourth over 3x to the fourth. And if I plug in a negative infinity, that's still going to give me this answer of 1. So this one happens to be both a right and a left end behavior model. So what I'd like you to do is in example 4, determine what the end behavior model would be. What does this simplify down to be that could model this function? So for that first one, I get 2/3 x cubed, and for the second one, we get 2/5. If we ignore all of those other ones, because as x gets infinitely large, they become really insignificant. So last but not least, we actually have to show some of these are right and left end behavior models. So this function, x plus e to the negative x, if I were to graph that function, so x plus e to the negative x, and we graph that. I kind of like this one. So they're saying we're going to prove that x is the right end behavior model and e to the negative x is the left end behavior model. And so when I look at my picture, I can see that. This kind of looks like y equals x over here, and this kind of looks like a backwards e to the x. It's an exponential type of a function, so e to the negative x. So on the picture, it kind of verifies that, but it says we have to show. So showing means we have to do the limit work. So let's do right end behavior model first, so the right-hand model. So we're going to do the limit as x goes to infinity, and they said to put f divided by g. So I'm going to do f of x, x plus e to the negative x, divided by x. Now I'm going to break that limit up. Notice I carry that limit notation all the way through. Now x divided by x, that's 1. 1. Here's where things get a little tricky though. E to the negative x over x. This negative exponent means bring it to the bottom. So another way of thinking about this one is 1 over x e to the x. So what happens when I plug in an infinity? I get this huge number on the bottom. So it's 1 divided by a huge number. So when I have low divided by high, then our limit is 0. So this whole term goes to 0. So 1 plus 0 is 1. And our hope was to get an answer of 1. That proves that x is a right end behavior model. So I'm going to say, therefore, x is the right end behavior model. Sorry, hard to write without holding the paper. So now we have to do the same thing for the left-hand side, but instead we're going to do the limit as x goes to negative infinity. Still going to put x plus e to the negative x on top, but this time they told me to use e to the negative x as my model. So again, I'm going to break it up. So x over e to the negative x, and then e to the negative x and e to the negative x. So this time, this one's going to go to 1 because that's the same thing. Now, before I use my negative exponent rule, I want to be careful here because I'm plugging in a negative infinity. So when I do negative infinity, I get a positive infinity. So I want you to notice I've got an infinity over an infinity. This is where math gets a little tricky. Which one of these is a quote-unquote bigger infinity? Which one grows faster? Does the function y equals x grow faster, or does an exponential function grow faster? So this one we have to take into consideration that it's e to the infinity. This one grows faster. So again, we have this smaller value over a bigger value, which means that this whole thing is going to 0. So 0 plus 1 is 1. So therefore, e to the negative x is the left end behavior model. And you're done.